load. Because we're in Canada, it can be Newton or pound force. And then L0 is the original length. It can be meter or inches. A is the cross-sectional area. It can be meter squared or inches squared. And the last one, E, is for your Young's modulus. Where it's in Pascal or pounds per square inch. Okay, so just to give you some code of Young's modulus. So Young's modulus in steel is equal to 200 to 210 gigapascal. Young's modulus of aluminum is between 70 to 72 gigapascal. Now, Young modulus of brass, the three most commonly used material, is about 110 to 115 gigapascal. Okay. So now the question is this: how did they derive this formula? Okay. Why it's important to know how they derive this formula? Then you will understand when to apply. If we don't know how the formula has been derived, we will not know when to apply. I used to be very ignorant. Okay, I apply this formula whenever I like. That's wrong. Okay, don't be ignorant like me. Okay, so how do they derive this formula? Okay, after I've derived this formula, we'll go for our first break. Okay, so when they derive this formula, they focus on under Axial loading condition only. Okay. Hey, sorry, it's my computer that's playing up. Here is back again. Okay. Under Axial loading condition only. Okay. Hold on, I will check something. Okay. Usually when the computer does that, it will screw up my notes. Yeah, it looks okay now. Okay. So under Axial condition only, right? So I'm going to draw the figure now. Okay. So we have again fixed to the roof. Now ceiling. This is our structure. Our structure is not under any load now. Okay. So the distance from here to here this is our L0. Okay. Over here, this is our A, which is our cross-sectional area. Okay. So there's no load. Okay. So no load. And I'll draw our centroid. Okay. I'll draw our centroid. So this is our centroid. Then the next diagram that I'm going to draw on the side is the same thing, except now there's a load. Okay. So we apply a load. Okay, so now we apply a load, which is our Py. Okay, so coming back to our transformation again, X, Y, rotation both Z, and it's applied on the centroid. Okay, along the centroid. So when the load is applied, right, we have a change in length now. Okay, we have a change in length. So the distance from here to here is L1. Okay, and then over here is where what we have is delta L. Okay, over here is our delta L, which is equal to L1 minus by L0. Okay, which is equal to our L1 minus by our L0. Okay, so this is also equal to our delta. Okay, our deflection. Okay, so all this is the material is in the elastic region. Okay, so the change in length is because of the applied load in the elastic region. When the load is removed, it will go back to its what? It has to go back to its original geometry. Okay, so now in the elastic region,
Sir, sorry.
yes,
Is it possible to stay zoomed out while you do the notes, just so
I,
that?
I, I, I can't because of the writing.
Okay.
Okay, I'll try to not zoom in and out so often. Okay, so in the elastic region, the material have to obey Hooke's law, right? In the elastic region. So now I'm going to draw the stress strain curve just in the elastic region. Okay, just in the elastic region. So this is stress. No, this is strain. This is stress. Okay. You have a straight line, right? So over here, the gradient is your Young's modulus. This line, the function is stress is equal to E epsilon. Okay, the stress is equal to E epsilon. Okay, so based on Hooke's law, right, we know that stress is equal to E multiplied by epsilon. Okay, so I'm going to call this our equation number 1. Okay, so let's determine how do we determine stress. Okay, so we know stress is equal to force divided by area. Okay, so this is very obvious. You'll say, yeah, I've seen this before. So this is your equation number 2. Strain is equal to L1 minus by L0 divided by L0. Okay, And this can be written as delta divided by L naught. So this is our equation number 3, right? So the next thing that we're going to do, we're going to substitute 2 and 3 into equation number 1, right? So we have P over A is equal to delta or E delta divided by L naught. And then finally, delta is equal to P L naught divided by AE. Okay, so we have derived the expression now. Okay, we have derived the expression now. So we're going to, once we have derived the expression, okay, so I'm going to call this equation number 4. Okay, so equation number 4 is only valid, okay, it's only valid in what situation? The first situation is material is under axial loading only. Okay, and I'll tell you why. Okay, why under axial loading only? Because if you look at how we started deriving it, the diagram we have drawn over here is only valid under what? Axial loading condition. Yes, if you have bending, torsion, this formula is no more valid. Okay, and then the next thing is when the stress in the elastic region material must have a linear stress strain relationship. Okay, stress strain relationship. So why is that? Because we have to apply what? We have to apply Hooke's law. And if you look at Hooke's law, stress and strain has a what? Has a linear relationship. Okay. The next one, which is not very obvious, is that the stress or the strain induced must be small. Okay. The strain induced must be small. Okay. So why is that? Okay. So if you look at most of material, right, stress is equal to E epsilon, right? So if we look at standard steel, the yield, okay, so the yield, let's look at our table. Okay, let's look at the table. The yield is about 250 megapascal. Let's look at I did not copy the standard material. Anyway, let's look at titanium. Titanium is a strong material. Okay, we're not working on titanium, we are working on steel. So steel, I can give you approximate. Okay, steel is about 650 megapascal. Okay, so steel at 650 megapascal is usually in a range of AISI 1045. Okay, the Young's modulus will be about 200 gigapascal, for example. Okay, So if you look at the yield, at the strain, okay, so strain is equal to stress divided by Young's modulus. So this is about equal to 650 times 10 to the power 6 divided by 200 times 10 to the power 9. Okay, so if I were to write down 650 power 6 divided by 200 power 9 is equal to 0.00325, or multiplied by 100, 0.325% strain. So it's very small. Okay. So what I propose now is we go for a 15 minutes break. I'll see you guys at 10:45. Okay. And there's a particular student. Let me stop recording first.